Okay, in this lecture, we're going to talk about isothermal reactor design. The generic species balance equation, these are commonly known as design equations and usually presented for specific reactors. But we can really start for any reactor configuration and think about an accumulation on the left-hand side, a flow in term for species I, subtract away a flow out term for species I, and then sum up all of the rates at which each reaction K is making species I. So that's what these terms over here are. Oops, I didn't mean to erase that. And then multiply by the reactor volume. So we can take this generic species balance equation and we can write it as a balance equation on a specific finite volume as shown in this diagram, or we can also write it for a differential volume, and that will give us useful equations to start for things like plug flow reactors. So all of the design equations, it's important to realize, are really just special cases of this one species balance equation. But most of the time we're going to be dealing with one of three basic kinds of reactors. We'll talk about batch reactors, plug flow reactors, and continuous stirred tank reactors. So a batch reactor is basically a container with no inlet or outlet streams. Typically, we're going to make the assumption that it's well stirred. Of course, it has no flow in or flow out. And whether it's constant volume or constant pressure, isothermal, adiabatic, this depends on some other details of the reactor that we're going to get to in some of the examples and in the next chapter on energy balances. To use the batch reactor design equation, first of all, where does it come from? If we go back to the general generic species balance equation, and we consider the case of a reactor with no flow in and flow out streams, so these two terms drop out, and we're left just with this equation right here. Okay, so this on the left-hand side, you can check the units, moles of species I per second. On the right-hand side, we have moles of species I per volume per second in the reaction term, and then we multiply it by volume, and so everything checks out here. To use this, we usually have to convert the rate expression and the number of moles of species I into functions of the conversion or the extent of reaction. Okay, so let's see how that looks in practice. If I is the reactant A, then if we do this in terms of conversion, in our stoichiometric table, we would find N sub A is N sub A naught times 1 minus X. And then when we plug that into our species balance equation for the batch reactor, the differential dNi dt would become minus Na naught dx dt. And on the right-hand side, we would have a function of the conversion, which of course depends on what kind of reaction you're looking at and what its rate law is, multiplied by the volume. You can do all the same analysis in terms of extent of reaction. There you would write that N sub A is N sub A naught plus the stoichiometric coefficient of species A multiplied by the extent of reaction. If you also relate the rate of generation of species A to the overall rate law, overall rate multiplied by the stoichiometric coefficient, then those factors of the stoichiometric coefficient drop out, and you end up with the derivative of the extent of reaction with respect to time is the rate in terms of the extent of reaction multiplied by V. Okay, so often what we have to do here, the task ahead of us is to compute the time that's required to reach a specified conversion target. Okay, so if we assume that V is not an explicit function of time, it can be, for example, if you have a reaction happening in a piston chamber. But here we're going to assume that it's not a function of time, except perhaps because X is a function of time and V may depend on X. But the idea is basically to separate variables and integrate this thing. So dt is going to be equal to Na naught dx over minus RAV. We can integrate all of that. And this is often quoted to be the design equation for a batch reactor. So it's basically just the integrated version of the thing that I called the design equation up here. So let's go ahead and do one example, see how this integration works. So what we're going to do is determine the time required to reach 80% conversion of 7.5 moles of A put into a 15-liter constant volume batch reactor. Okay, so the reaction is first order in A, and we have this given rate constant. All right, so now if we go through and we use that integrated design equation, so this is T sub x is Na naught, integral from 0 to x dx over minus RAV. That's going to be our starting point now. V is constant, so we can pull it out of the integral. That makes Na naught over V, the concentration of A at the initial time. And inside the integral, we have left dx over minus Ra, which was just Ka times A. All right, but A is equal to A naught times 1 minus X. And so we end up with two factors of A naught. They cancel. And now our whole integral, after moving the rate constant over to the left-hand side, is an integral of dx over 1 minus x. This integral can be done pretty easily, ends up giving you minus log of 0.2, and now multiplying or dividing through by the rate constant, Ka, you get the time to reach 80% conversion is 32.2 minutes. What did we do graphically? Visualize what you're doing in these integrals. What we're doing is integrating minus Na naught over Rav. Of course, this is really a pretty complicated expression in here. But what we do is we go through and we integrate that versus x, and the area under the curve up to the desired conversion identifies the time that it takes to reach that level of conversion. So this procedure is called a Levenspiel plot, and there are Levenspiel plots for analysis of batch reactors, for analysis of plug flow reactors, and for analysis of CSTRs. Okay, another example of a batch reactor problem. In this case, we have a reaction A plus B goes to C, and the rate law is K times the concentration of A times the concentration of B. The rate constant is almost 10 times 10 to the minus 3 liters per mole per second at 25 degrees C, and we're going to find the isothermal constant volume batch reactor volume that we require to produce 175 moles of C per hour with conversion level of 90%. And we're going to assume when we do this that the initial concentrations of A and B are the same at 0.15 molar, and that the downtime between batches is 30 minutes. Okay, this is a typical thing that you have to take account of. And what we want, we have a target production rate, and so we have to think about how long each batch takes, how much each batch is going to make, and what the downtime is between batches. Okay, so the first thing we're going to do is start with the stoichiometric table. We have species A, B, and C. We have constant volume, so we can do this in terms of concentration is no problem. The initial concentrations are given here, A naught, B naught, and 0. And then those are going to become A naught times 1 minus x, B naught times 1 minus x, and A naught x. Of course, B naught and A naught are the same. Now, that target production rate, I'm going to call it, it's almost like an average flow rate. So I put a little bar over a flow rate kind of symbol here. So this is F sub C averaged over a batch is 175 moles per hour. And that's going to be the amount of C that we make per batch divided by the total time required, counting the downtime between batches for each batch. Okay, and then if you look at that expression, you see that all parts of this are given in the problem except for one piece, and that's the time to reach 90% conversion on a single batch. Okay, so from here, we can go in and we can begin to compute that time to reach 90% conversion. So we go back to our integrated batch reactor design equation, and we get the time to reach 90% is the number of initial moles of species A, integrate from 0 up to 0.9. That was our target conversion, 90%. We have dx over minus Ra times V. What is Ra? Well, the rate law was K times A times B. We can write those in terms of conversion as A squared, A naught squared times 1 minus x squared, one from the A and one from the B. And the rate law is, of course, we're consuming species A, so the rate is minus the rate of generation of A. That's to ensure that we're getting a rate of consumption of that species. All right, so now we can fill in the parts. I've simplified some of the algebra quickly. Pause here if you want to go through this. But basically, when you plug these constants in, and remember that Na naught over V is going to give you one more factor of A naught. One of the factors of A naught's canceled, but then you have another one. You can pull it out, move it to the left. Now this is K A naught times time to reach 90% conversion is just equal to an integral of pure numbers, and that integral comes out to be 9. Okay. And then you unravel all of these constants in here to get the T 90%. Basically means divide 9 by K times A naught, and you get 1.68 hours. Now, we can go back to this expression here, and we can plug in our answer for the 1.68 hours goes in here for the T 90%. These are all the numbers filled in down here, and the answer comes out to be 2,830 liters.